This is section 3.3, and what we want to do is just look at this idea of increasing or decreasing and checking for relative max and min. And so again, you know, as we try to do in this, we're trying to look, mostly we're looking between two aspects of mathematics: graphical aspects and algebraic aspects, and trying to match those up and see what's going on. And so we've seen the idea of critical numbers or critical points, and you know, if I'm looking for, say, a relative maximum on my function f, you know, I'm looking for that spot, that critical number where f prime of x equals 0. And so, you know, there we can tell. Now the problem with a relative max or min is we can't just ask its height, okay? Because a relative max or min, we don't really know, you know, just because the derivative is 0, you know, and we get a value there, we may not have anything to compare it to as far as another value, and because we're not necessarily on a closed interval, and so we don't really know what's happening outside our little neighborhood of things, and so we're really just looking in the neighborhood of what's going on whenever we talk about the relative max and min, and so we're still going to, you know, look for these critical numbers like this. But now we have to kind of ask, well, okay, how, when I look at this picture, one of the things I notice is at a maximum, yeah, the derivative appears to be 0, or maybe is undefined if the function's not really well behaved. And, you know, so there's a possibility. But then what else am I seeing? And for a maximum, you know, what I see is the function, in getting to that maximum, as I come in from the left, it's increasing, it's getting bigger and bigger and bigger, and then it hits that maximum, and then it's decreasing, it's getting smaller and smaller and smaller as I move from the left to the right. And so, you know, what do we mean by that algebraically? And a function f of x is increasing on an interval say AB, notice it's an open interval. I have parentheses, not square brackets. So a function f of x is increasing on an open interval AB if for a less than x1 less than x2 less than b. So I'm just saying that the x1 and x2 are inside here somewhere. If for those x1 and x2 and x1 smaller than x2, then f of x1 is less than or equal to f of x2. Now it's strictly increasing if there's no possibility of equality there with the strict inequality there. But it could be increasing, but not strictly increasing. So it could be sort of flat for a while, something like that. And then similarly for decreasing, right? I'm just going to write decreasing on our interval AB if again for a less than x1 less than x2 less than b, what we have is that f at x1 is greater than or equal to f at x2. Okay, and so that's what we have on our definitions. So let's see. So then, how do we use calculus to test for that? And well, here I've got a function that's increasing. Look at the tangent lines at any of these spots, and we see that the tangent lines have positive slopes, and so we have that f prime of x is greater than 0. And then similarly here, if we've got something that's decreasing and I start looking at tangent lines, those tangent lines have negative slopes, and so f prime of x is less than 0. Okay, so here we have increasing and decreasing. And we know that f is increasing on AB if f prime of x is greater than 0 for all x that are elements of that interval AB. Okay, and then similarly that f is decreasing on AB if f prime of x is less than 0 for all x element of AB. And, well, it could also be constant on that whole thing. F is constant on an open interval AB if f prime of x equals 0 for all x element of AB. Okay, so now, I could take some function, let's take something simple, and if I look at, say, f of x equal x plus 1 squared. So there's a pretty simple function. Now I can tell you where f is increasing and decreasing and where it's got a slope of 0 simply by looking at the derivative. So I'll take the derivative. Now this is a chain rule. I have 2 times the outside 2 times x plus 1 and then times the derivative of x plus 1, but that's just 1. So we'll just get 2 times x plus 1. And now, I can look at, well, where is f prime of x equal to 0? When does that happen? Well, that's when 2 times x plus 1 is equal to 0, or x plus 1 is equal to 0, or x is negative 1. Okay, so that's the only time it's 0. And so what I want to do is kind of look along the number line here. Here's negative 1. And then I want to look here for x less than -1, and I want to look out here for x greater than -1. Another, interval note. So here I've got an inequality notation. Interval notation, I'm looking at -infinity to -1, that open interval. And here I'm looking from -1 to positive infinity. Okay, so I know that f prime of x, doesn't change anywhere except at x equal -1. And, so we have various ways to decide, what the sign of f prime of x is. But, one, I could set it up as an inequality, right? I could just say, well, solve 2 times x plus 1 is less than 0. Okay, divide both sides by 2. That doesn't change the inequality, so that's fine. And then x is less than -1. Okay, so we have that f prime of x is less than 0 for x less than -1. Now, another way I could do it is, again, I've got these intervals. I could just take something in those intervals, since I know f prime of x can't change anywhere in there because there are no other critical numbers for which to change at. I could just put in 0, so I could just look at, for instance, f prime of 0 is equal to 2 times 0 plus 1, and that's 2, which is greater than 0. And so that would tell me that on that interval, I have f prime of x is greater than 0 for x greater than -1. Okay, so there are various ways to come up with these sorts of things. And so if f prime of x, if I'm kind of thinking about what's happening at -1, now I'd have to evaluate f of x at -1 to get its value. But let's say I put it right there. I don't have a y scale, so it doesn't really tell me what it is. But it says if I'm less than -1, the derivative is negative, or in other words, I'm decreasing. And then for x greater than -1 here, it's positive, and so it's increasing. And so my function x plus 1 squared must look something like that. Okay, and I know it's a parabola, and I know it opens up anyway just from my pre-calculus days and all that. But there we go, and so I have a relative minimum. Okay, and so this is the idea of increasing and decreasing and using our critical numbers. And that's pretty much what we're doing in section 3.3 is, we're really just looking at this sort of stuff and asking, can I translate between a nice picture like this and my algebraic representations of derivatives to help me out with that. Okay, so that is what we're doing in 3.3, and we'll call it good for this video.